I believe this is where we left off last time for the acid-base videos. I wanted to do a couple of example problems. If you haven't written down this box, pH box, hydronium hydroxide POH box, this is how you convert from one thing to another. A little map for you. Put it on the back of your mole map. First, I want to do a strong acid problem. Which is basically using that box. So here we have calculate the pH and the OH minus of a 5 times 10 to the negative third molar perchloric acid solution, or actually it's called chlorous acid solution. And so we can think about this reaction as being this acid HClO4 aqueous, just put it there, plus water, aqueous as well, or liquid. I'm going to put just one arrow, right? And I'm not going to put both ways because this is a strong acid, which was, if you review what a strong acid means, is it completely dissociates. It exists as the products, none of the reactants, as opposed to weak acids, right? And so when it dissociates, this hydrogen is given to this water. That is a 2. And so this becomes H3O plus, has an extra hydrogen, plus the anion of the ClO4 minus, right? So that's the reaction. We have, in the strong acid, we have 0 of this. We have almost, or 100%, very close to 100% of this. Okay, so this doesn't really exist. Okay, and of course, when you write this out, you usually simplify this. So if we know that the concentration of this acid is 5 times 10 to the negative third molar, we know that is actually the concentration of the H plus, right, the hydronium, which of course we can abbreviate this all to simplify this and make this H plus. Anyway, right? Makes it a little bit easier. Okay, but we simplify it and write it as that H3O is H plus. So that's what we're looking for. That's because it's a strong acid. This is how it exists. This is the concentration of that. Okay, and so if we look back at our map here, if we know the concentration of the hydronium is the H plus, and so we're going to take the minus log of that to get the pH. And so we want to take the minus log of 5 times 10 to the negative third to give us what our pH is. Right? This would be on the pH scale. Okay, so if we take out trusty calculator, open that up, you can see that we want to take the 5 exponent 3 negative. Every calculator is different, so make sure and we want to take the log of that, and of course we change the negative sign, make that positive. Okay, so the pH of this would be 2.3. Right, this has one significant digit, 5, right? And so for pH, remember this first number is not because it's a logarithmic scale, is not part of the significant digits. That 2 counts for this exponent. The 3 is so this would be 2.3 pH. Okay, and then if we wanted to find the hydroxide, right, we already know the H plus is the 5, and so we can look at our box again, and we want to find the OH minus because we know the H plus, and they coincide. They basically work together in any acid. You always have this ratio of the hydroxide and the OH minus. So we want to take 1 times 10 to the negative 14th divided by or on this side, the hydroxide, the hydronium ion. So go back over to our calculator, and that would be 1 times 10 to the 14th negative divided by 5 exponent 3 negative equals. And so It should be much smaller, right? Because this has a pretty high pH. That means you have a lot of the H pluses, not as much, you have much less of your OH minuses, and so of your hydroxide, and so this would be 1, 2, 3, 4, 5, 2 times 10 to the negative 12th. Okay. And if you wanted to, you could figure out the pOH of this, the amount of hydroxides. Okay, so for a strong acid, anytime you have a strong acid, you're just using that box, okay, to figure out those things. And you can be asked for the pH, the OH minus, you can be asked for the hydroxide, you could be asked for the pOH, you could be asked for any of these four things with the strong acid, and it's always just going to be changing that concentration to pH, okay. So it's a strong acid. For weak acids, there's some things, there's a list of things to help you solve them. List the major species in the solution, so write out the reaction, choose what are going to be important. Then you have your K values, which I gave you a list in one of those notes, but it's also appendix 5. It's right after the thermodynamics information, but on it's appendix A22. A22 in the back of your book. You can actually find a bunch of equilibrium constants for acids, monoprotic acids, okay? Sort of write out this equilibrium expression, right? I'll show you what that is. I kind of showed that in other videos. Ka equals that ratio, right? The expression is just that ratio. And then what you're going to do is you're going to make a chart, right? It's often called a ice chart or a rice chart, and so rice, ICE, and I actually just write, when I do my chart, I actually write like this, and so the R stands for reaction, so you actually write out the reaction, then you put down what the initial measurements are, then you have some kind of change is the C, okay, and then you have at the end or after equilibrium is reached, what will all the concentrations, pHs, measurements be, all the set of variables, okay? I'll show you that in more details. Once you find out the equilibrium, you find that unknown, you find your concentration of your H plus, right? Really, if you're trying to find acids, you would take the easy way, right? And you do what are called the 5% rule. I'll show you that. Essentially, if your answer is 5% of your initial, then you can just use that as your answer. And it's a way it simplifies things, and then you can calculate pH and pH from that chart. Okay. So first, probably today, I'm only gonna have, for this video, I'm gonna have only time to do one where you don't have to think about the 5% rule, or sometimes it's called the small x approximation, okay? Hopefully I haven't even enough time on this video, okay? So here we have this acid here that's called hydrocyanic acid, right? I have the cyanide anion with hydrogen, okay? And so this is going to have your acid at this concentration. This is your initial concentration. This is where you start with, okay? It's going to be mixed with water, of course. It's going to be aqueous. I'm not going to put the states of matter. It's actually, because it's weak, I'm going to draw it as this bigger area. You don't have to do that. It goes both directions. And then, of course, we're going to make this H3O or H plus and our ion, okay? So what we want to find is the concentration of this H3O or the H plus. So for my reaction, or that rice table, you're going to write out your reaction. And so I'm going to simplify it. I'm going to leave this off, and I'm going to leave off the H3O just to make it easier. So you have your, because they're not really doing much, right? So you have your HCN, you have your reaction there, you have your H plus, and you have your ion, okay? And these are really what we're worried about, okay? And so initially, to start, that's what is given here. To start off, you always start with this concentration, this molarity of the acid. That's always given the problem. That's what you measure out. Okay, and so this would be 0.100. Okay, that's to start initially. All right. Make a little table here. The initial of these, but this is before this dissociates. So at first you have 0 or about 0 of these. You might have a little bit of H pluses, but not enough to account for. Okay, then you're going to change. So this is going to go up by some amount because this is going to, for every one of these, they're going to have one of these dissociated and one of these. So this is going to go up by some amount. That's your unknown. How much this is going to dissociate. That's what we're trying to find. So this is going to go up. It's going to change by plus x. This, of course, is going to be exactly the same because for every one of these, there's one of those. Okay, this here is going to go down by that same amount. Okay, so that's your unknown. That's our x. Okay, and then for equilibrium, this is going to be 0.100x or minus x because it's going down by that much. This is going to be x, and this is going to be x. Okay, so there's my rice table. I'm just going to make this a little bit smaller so I have a little bit more room. So my rice table, maybe. It's a little bit smaller. And so my equilibrium expression was the next thing to do on there. And so my equilibrium expression is my Ka, and it's always going to be this, is your concentration of your ion, H plus, okay, times the concentration of your anion, in this case it's Cn minus, okay, and we're going to divide by our concentration, our initial, our molarity of our acid, HCN, okay. And so we're going to put in these equilibrium cones here. So I looked up on the chart, and so this acid has a Ka of 6.2 times 10 to the negative 10th. Okay, the book I actually got this problem out of had 4.9 times 10 to the negative 10th. It should be the same. Check what your book says. You can just use that. It's pretty much the same. So I'm going to use this. So that would be 6.2. This is going to be x. The Cn is going to be x. This is going to be 0.100 minus x, right? And so my Ka is this. So what I know what I have is this is my equation, 6.2 times 10 to the negative 10th is equal to x squared, I'm going to multiply those, divided by 0.1 molar minus x, okay? And so if you can see, if we're trying to solve for x, we have basically a double Pauli, what's it called? We have basically can use the quadratic equation. But what we're going to do is we're going to simplify this first, make it easier. What we're going to do is we're going to imagine that this x is so small that even when you subtract it from 0.1, it's really not going to make much difference, especially when we round it to the nearest significant digits. Okay. So what I'm going to do is I'm going to ignore this. I'm going to say this is so small, I'm not even going to notice this. And so now what I'm going to do is just cross multiply. So 0.1 times 6.2. So I'm going to do that, 6.2 exponent 10 negative. I'm going to multiply that by 0.1. So it's just going to move the decimal, right? Would that be? So that's just going to be 6. Go back to my original color here. 6.2 times 10 to the negative 11th is equal to x squared. So now I'm just going to take the square root. I don't have enough time here. So I'm going to take that number, take the second function, that. So that's 7.87 times 10 to the negative 6. 7.87 times 10 to the negative 6. I only have a minute left in this video. So what you want to do is you want to take that and compare it to this original up here concentration, right? So and then see if that's 5%. So I'm going to take this number and divide it by 0.1, and that gives me a small number. Multiply by 100 to put it into a percentage, and so that gives me 0.078%. So that's smaller than 5%. As long as it is less than 5%, then you don't have to worry about doing the quadratic formula and solving for this x. It is small enough. So 7.87 times 10 to the negative 6 would be your answer. That would be the concentration of your H+, which then